Hey everyone, in this video we're going to take a look at annuities. And an annuity is just a system of regular payments or deposits. For us, our payments or deposits will be made into a compound interest account. And there are two types of ways that this can be done. One is called a regular annuity, which is the type that we'll be examining. That's where the payments or deposits are made at the end of each compounding period. The other way that's considered is called an annuity due. That's where you make the deposits at the beginning of each period. And so for us, all of these examples will be for regular annuities. Note that annuity due has a totally different formula. So nothing that we say here will work unless you adapt it to annuity dues. Okay, so some basics about annuity accounts. The general principle is money builds over time because it is a compound interest account and you are making regular deposits into it. So not only do you get the money that you deposit into it, but you get the interest that accrues as well. And since it's a compound interest account, that time really plays into it. So here is our formula. It's pretty complicated. There are a lot of variables in it, so I just want to go through real quick and identify each one. So this piece of n, this is called our future value. And the future value is the amount of money that will be in the account after n years. So in other words, we can call this the amount after n years. So that means you've been making these regular deposits, you've been accruing interest for n years. How much money is in there total? D is the deposit, or sometimes called the payment. So that's the regular deposit that you make, which means that at the end of each compounding period, that's how much money is placed into the account. K is the compounding period. That's the same as we had in compound interest. And R is the interest rate, and it's what we call the nominal rate, which means it's the rate given for the account, and then that interest rate is broken up into k different compounding periods. I should mention here the compounding period is however many that you have in each year. So like let's say you compound monthly, then k would be 12. Let's say you compound daily, it would be 365. And then this capital N up here at the top, this is the number of years. So you have 5 variables. You have the future value, or how much will be in the account after n years. You have D, the deposit. That's your regular deposits that you make into the account. You have K, which is the compounding period or number of compounding periods per year. And you have R, which is the interest rate, that's your nominal rate. And then you have N, which is number of years. So now on to the examples. Our most straightforward example will be solving for future value. So here's our setup. You want to save $400 per month, and that money you take and place into an account. Your account is a compound interest account, has a nominal rate of 1.25%, and is compounded quarterly, which means 4 times per year. So our question is, after 8 years, how much money is in the account? So we need to use our formula, and just in case you don't remember it, I'm going to write it here. So it's the future value is equal to the deposit times this big messy fraction, which is 1 plus r over k raised to the n times k power minus 1, all divided by r over k. So we need to identify what we're solving for. And this question is how much will be in the account after 8 years, so that's definitely a future value problem, which means we have to plug in everything else. So our piece of n here is our D, but now we need to notice before we just plug in D that our deposits are made each month, but our compounding period is quarterly, and so we need these two things to match up. So first, before we can use this formula, we have to convert our monthly payments into quarterly payments. Or deposits. So that's fairly straightforward. If we save $400 per month, but we want to know how much we save per quarter, a quarter is a fourth of a year, so that's 3 months. So I need to take my monthly payment, 400, and multiply by 3. So I get 1,200. So my deposits are actually 1,200 per quarter. And that's how I consider them, not 400 per month. So now we can plug this stuff in. So we have 1,200 is our deposit, and this is 1 plus R is 1.25%, or 0.0125. Compounded quarterly means 4 times per year. We have 8 years, and we compound 4 times per year, and then divided by this R over K expression. So this is what we need to plug in. Beyond this point, it becomes an algebra problem, and there's a lot of calculator manipulation that you need, but I'm just going to show you just a few of these steps. So we're going to take our 1,200, and 0.0125 over 4 plus 1 comes out to be roughly 1.003125. And that's raised to the 8 times 4, which is 32, minus 1. And then this same 0.0125 over 4, without adding the 1, is 0.003125. So these things need plugged in, and we get an approximation, so I'm going to leave the 1,200. I'm going to approximate this numerator, which is about 0.10499,861. And the denominator, unchanged. So then we can collapse these things, and we get, that's about 1,200 times 33.599,55439. I'm keeping a lot of decimal places because I don't want to lose things in rounding. And so in the end, this is approximately $40,319.47. So after 8 years of making these $400 monthly deposits, after all the interest is accounted for, we have roughly $40,000. So we may ask a follow-up question. We've made all these deposits and we've turned this money, given time and interest, into a lot more money than what we deposited. How much actual interest did we accrue? So our question is, how much of this 40,319.47 is interest? We don't have a formula for this, but we can think our way through it and realize that in total, at the end of these 8 years, we had $40,319.47. But some of that was money that we deposited, and then the other part of it is interest. So we need to find out, how much did we deposit? So the total amount of money minus our deposits must be the interest. There are only 2 ways that money gets into an account. It's either deposited or it's interest. So for our deposits, let's compute that. So our total deposited is $400 per month, but that took place over 8 years. And so that's times 8 years, but there are 12 months per year. So that's 400 times 8 times 12. And this comes out to be $38,400. So I'm going to take this and plug it in up here. So I have 40,319.47. That's how much we ended up with, minus how much we deposited, which is 38,400. And that's the amount of interest that we accrued. So that is 19,1947. In other words, we accrued around $2,000 of interest over these 8 years. And so that solves that problem. So this, again, is an example of solving for future value, and then our follow-up question was solving for how much interest was accrued in the account. So for our next example, we'll be solving for the deposit. So here's our setup in this case. Say that we're saving up for college, or more likely you're a parent and you're saving for your child's college, and you want to save $200,000, and you have 15 years to do it. So you find this account that gets 9% interest compounded quarterly, and the question is, how much do you need to save per month? Because probably you get monthly paychecks or something. You need to know how much of that paycheck you need to take out and save in order to reach your goal of $200,000. So in this case we use the same formula, but it looks a little bit different. Since we're solving for deposit, that means we're solving for D. So our P sub n is now 200,000. That's the amount that we want at the end. And so if we set all this up, it's going to look pretty similar to our last problem, just different letter to solve for. So we get 0.09, that's our percent over 4, compounded quarterly. 15 years, compounded 4 times per year. So that's what we're looking at. So I'm going to go through how to solve this, but you can imagine how it's going to go. We're going to take things from one side to the other. Eventually we're going to get D by itself. So the first thing I'm going to do is take this denominator, this 0.09 over 4, to the other side. And that's D times all this stuff that's in the numerator. So then I can take all this stuff in the brackets and divide that, since it's multiplied to D, I can divide that to the other side. And notice nothing's plugged in the calculator yet. I'm just going to set it all up, and then we'll plug it all in. The 15 times 4 is 60, so I'll just replace that exponent with 60. Notice that's the 15 times 4. That one over here. And now, type it in. So at this point we're going to be doing an approximation. The numerator, 0.09 divided by 4 is 0.0225. That's still times 200,000. So this 1 plus 0.09 over 4 is 1.0225 raised to the 60 minus 1. And now that I think about it, I don't think this is approximate right now. This should be equals. But anyway, we'll approximate at the next step. So we get, after multiplying out 200,000 and 0.0225, we get 4,500. And in the denominator, we get this decimal. And that is definitely an approximation. So what this ends up being is D is about 1607.07. And it looks like we've solved our problem. However, this isn't quite the answer that we're looking for, because our account compounds quarterly, which means that this D is a quarterly deposit. But our question says how much do we need to save per month? So if we know how much we need to save per quarter, that's per 3 months. So we need to change that 3-month savings into 1 month. So in order to solve the problem, we just take our 3-month quarterly savings and divide by 3. And so this is about 535.69. So this is our answer. So we want to save this per month. And that in 15 years, these deposits per month will get us to our 200,000. So that's solving for D, or deposit or payment. Now let's look at an example where we solve for time. Okay, so this one is going to get pretty rough in the algebra. But here's our setup. We have an account that has 5% nominal interest rate. It's compounded yearly, and we pay $100 per month into the account. And our goal is to reach $20,000. So if we pay $100 per month into this yearly compounded account, how long do we need to save to get to $20,000? So again, we use the same formula, but now how long means we're solving for capital N. So we want to reach 20,000, which means that's our future value, P sub N. We're saving $100 per month, but the account is compounded yearly. So first, we need to change our monthly deposits into yearly deposits. We have monthly deposits, we need those to be stated as yearly deposits. So our monthly deposit is $100, of course 12 months in a year, so we get $1,200 as our yearly deposit, which means our D is $1,200. And then to fill in the rest, we have 1 plus 0.05, which is our interest rate, over 1, because it's compounded yearly, so that's once per year, to the N times 1 minus 1, and then all that divided by 0.05 over 1. Okay, so now I want to get N by itself. I'll do as much as I can, but at some point we're going to hit a wall and we're going to have to use natural logs. So the first thing I'm going to do is notice that dividing by 1 doesn't do anything, so I'm just going to get rid of that, just to keep this looking as simple as we can. Also, multiplying N by 1 doesn't do anything. Okay, so that's what we're looking at. And the 0.05 I can take to the other side, multiply each side. The 1,200 I can divide, so I'm going to do 2 steps in one. I'm going to multiply each side by 0.05, and I'm going to divide each side by 1,200. To end up with that. Okay, this minus 1 can be taken to the other side, but I have to add it. So I have 20,000, so I have this whole fraction still. The whole fraction plus 1. And over here, 1 plus 0.05 is just 1.05 to the n. Now we get to a point where n is buried within the exponent. And so we'll use a technique that we've seen before, which is in order to get a variable out of an exponent, we'll take logarithms of both sides. And we'll choose natural log. So if we take natural log of both sides, it's natural log of this entire left-hand side equals natural log of the right side. And since this is natural log of something to a power, the power n can come out front. So I have n times natural log of 1.05. And then the natural log of 1.05, that's just a number, so I can divide that to the other side, which means that I end up with this same nasty natural log divided by natural log of 1.05, and that's equal to n. So mathematically, I would be satisfied with this answer. However, in real life, we need to get a decimal approximation. So I'm going to approximate the numerator and denominator separately, and I get roughly 0.6061358 divided by 0.04879016. And then finally, we get an approximation for this of about 12.423. That's our answer. So the original question was, if you save $100 a month in this 5% compounded yearly account, and you want to reach $20,000, it'll take you roughly 12.423 years. And that's the units for this. So that's about 12 and a half years. So solving for time gets pretty rough because you have to use natural logs. Note that these are natural logs, but you could have used any base for your logarithm that you want, base 10, base 2. I just chose natural log, personal preference, but you can choose a different one. Your answer will be exactly the same. Notice if you go back to our original formula, we didn't have a problem in this video where you solve for K or R. We'll assume that those have to be given to you. You can potentially solve for R. It just gets really messy, and we'll just assume that the rate and the compounding period are both givens in the account. Okay, and that's all our examples for annuities.